So many thanks for making votes. Hope you had nice long weekend. Sorry for bothering with materials during, but you can see that it's not too hard task. It's doable, and there is already one person in the class who submitted the slides, because it's like 4 slides, 4 minutes, not a big deal. So here is your votes, and I just connected them by lines, and here are the schedule. So if you are not happy with it, let me know, either publicly or privately. We'll arrange exchange, but I think it's easy enough so that everyone will be happy. So I think the box should be empty, and then I should either try myself or call someone from the class to write this equation, but we will not play this game right now because it's quite easy. So who we are and what are we doing? Sure. Oh, hello, Alison. Share the screen. Yeah, it is better. So we are in physical chemistry class. The goal is to interpret and predict results of characterization of molecules and processes, and the practical task for near future right now is to get hands wet with quantum theory, which deals about the nature of electron. There were no homeworks and practical assignments because this subject, unlike most of others, it's like stepwise. Before we accumulate certain critical mass of concepts, there is no reason to do any problem solution. And it may be not comfortable, and the subject is counterintuitive, but I hope you understand it and work cooperatively. So right now we are accumulating concepts, and we are almost done. Approximately starting from the next week, we can approach closer to more practical things, and there will be homeworks. Not that the idea that you or myself like homeworks, but at least we can try something practical rather than doing philosophical things, and make sure that we understand what we are doing, and comparing, like doing some little exercise and comparing this predetermined answer if you go in the right direction. So there is a concept of Schrödinger equation and wave function which determines probability. There is a concept of the total energy operator, which is set of derivatives, and there is a way to compose this energy. And here's the time derivative, so it's partial differential equation. And know that there is time, and it has time dependence. Today we will do a trick of removing time dependence because, and I'll provide justification. So often people need to characterize static situations when the system is not changing, and we just need to characterize its properties. And it is reasonable. So the Schrödinger equation without time dependence is kind of incomplete, but for many problems it is useful. So we'll do a legitimate way of removing time dependence, but still carry on some important characterization of materials. And then we will bring in another concept by getting which we all will be on the same page to go to your presentations. We will go to the concept of eigenstates, eigenfunctions, eigenvalue problem, which you may have seen in linear algebra or differential equations, but we will revise it briefly today. And then some of your presentations will be resting upon this concept. So it is something that we may want to have a general idea about. So I have two tasks for myself today. So remove time dependence and speak about eigenstates. Little thing that we did last time is I was trying to convince that swapping order of functions and operators is not innocent and needs to pay some price. And later on, we will have some practical and philosophical consequences of this. This is just the simplest example, which should keep our eyes open for the future. Okay, so something partially new. I think if we have no voice and no recording, online participants would protest. And if any of you are on Zoom in the future, if you do not hear voice, please type in the chat or raise your voice, because we need it. So yellow box, I think it is one of the postulates, and this equation, which seems simple enough to glance at and memorize, is one of another cornerstones of this quantum theory. So I cannot make ranking which equation is more senior, which is more junior. There is a minimal set of concepts and equations that we all need to practice, but this is not avoidable. And the meaning of equation is to set up a bridge between mathematical abstractions and real world. So the thing on the left, which is often symbolized by this angular bracket, is expectation value that one is measuring on actual experiments. It is something that one can measure what comes out of the instrument. And there is a language in colloquial language in quantum theory that anything that can be measured is called observable, because some concepts are not observable, they're mathematical abstractions. And typically they are related to things that we can touch, like position, momentum, intensity of emission for certain spectral line or stuff like that. So on the left, we have real world. On the right, we have combination of several abstractions. So the psi star, which means complex conjugate, right? We got it. Swap the sign in front of imaginary unit anywhere we see it. So wave function itself, wave function conjugate, and between them, this little hat on the top of symbol means that it is an operator. So for each observable, for each thing that we can touch in the real world, there is a mathematical abstract concept, the operator. And we can define the operator just based on this bridge equation. So such combination of derivatives and functions, such differential or maybe matrices, such mathematical object, by convoluting which these wave functions, we will get something that comes out of the instrument. That makes sense? If you would have like more time, maybe we will do exercise to write down it in your notebooks by the end. But I'll try to rush to the end and then see how we do it. But this is something important, and one of the presentations on Friday will cover it, maybe from slightly different aspect. So the simplest example, but please do not be decepted by simplicity, is position. Like coordinate in x dimension, if you just put the variable x, right? And then we know that wave function, when it is multiplied by itself, when it is wave function squared, it gives probability density, right? So if you multiply probability density by position and then integrate over all possible positions, it will give a mean value. Makes sense? Please confirm if it makes sense or we need more. Yes? Okay, good. And this is like maybe mathematically the simplest, but when one places different things, sometimes differential operators, one can get basically anything we observe in nature. And as we go through the course, or as you go through some textbooks, you will see a little dictionary vocabulary, which gives examples of this operator. So, and there is an analogy between things that people were operating before recognizing wave nature of electron, like one was using just variable. And then in this quantum theory, it is operator. And the first thing that we will maybe focus a little bit more today is momentum, which is like velocity times mass. And here is a very simple thing, but it is like first step on the counterintuitive way. So how would you design a quantum operator for momentum if you need to do that, if you haven't seen this table? Like I would think if like momentum is related to velocity, I maybe need to do the same way as intuitively, like velocity is derivative of position over time, and then I just integrate, right? It seems reasonable. But what we see in this quantum theory, it looks very strange at the first glance. So instead of, we need momentum, which is basically velocity, and instead of taking derivative over time, we take derivative over space, over position. So I wouldn't be surprised to see if anyone is surprised. So it is derivative over space. And if we use this derivative in the equation that sets us a bridge between abstract world and real world, it really will give momentum and velocity, and we'll discuss it and justify why it makes sense and why we need to do this. Anyone has an idea how to justify this strange definition, or any ideas why it is surprising and not right? Okay, I think it is too counterintuitive. I'll offer sometime, show some slides later. So we are slowly going to this quantum world, and we saw an example of potential wave function, possible wave function as the this spiral, right? Complex exponential. So if we just, as a learning example, assume this spiral complex exponential as wave function, which has wavelength and coordinate in this power, right? So it gives some fringes, it's complex fringes. Now, there is another thing that I'll justify later, or some of you may accept intuitively. If you look on the quantum of light, and who did operate the spectrophotometer or any spectroscopic instrument? Yeah, 1, 2, 3. Okay, and you have an idea because you compute spectra, right?
Yeah.
So which photon has higher energy? The one with shorter wavelengths or the one with longer wavelengths? What is more energetic? Infrared or X-ray? X-ray. And X-ray, is it shorter or longer wavelengths? Shorter. So the shorter wavelengths, the higher energy. And again, I'm not proving anything mathematically. Do not repeat it outside of the class. I'm just showing direction of intuitive thinking. So shorter wavelengths, higher energy. Higher energy, bigger momentum, because with higher energy you can fix something. Now on the other side, if we assume that wave function is this complex spiral, and we take derivative over position, the wavelength or 1 over wavelength will come outside of it by the practice of the derivative. And one of the wavelengths is related to momentum. So the idea that denser fringes means higher momentum, and density of the fringes will come out of exponential if you apply this derivative. Make sense? So those were language justification, and I hope to give more like mathematical rigorous things, but first impression could be the only one that we memorize. And for other things like three-dimensional momentum, energy, kinetic energy is really important. It's second derivative because it's momentum squared. And for now, it is enough. But later on, we will look through the rest of the table, and whoever presents appropriate postulate can just display it, maybe tell a few words more about this table, or at least remind it to everyone. So what are we going, and I didn't start the lecture. It was only introductory words. So what is the expected outcome of our meeting? So it would be really satisfied is if by the end of the meeting, everyone will feel happy and comfortable by looking on each line of the slide. Does anyone feel happy by looking on the slides right now? On the slide? Does anyone feels unhappy by looking at it? Okay, so my goal is to turn your thumb, or at least turn it halfway. So, do you see any? Do you recognize anything that? So, how many lines we have? 1, 2, 3, 4, 5. Which line you recognize as something you saw before, and you can get a general idea what it is? So, line 1, right? Everyone? Okay. Now let's look on line 5. Is it completely nonsense, or you can design some hypothetical ideas what it is? Completely no, or something? Okay, yeah, thank you for your feedback. So if you multiply by function on itself, it should give probability density. If you integrate probability density over the whole space, it should be 1 if you speak about one particle, right? One element. So if we know the wave function, if the index here and there is the same, it should be 1. But if by some reason we take different wave functions, if the electron in one quantum state, another quantum state, if you introduce this concept of quantum states, then this integral will give 0. So it's just a little awkward way to check if these two functions coincide or not coincide. And the name for this procedure is orthogonality. So it is practically used in basically all problems that later on are solved. Okay, so we are done with first and last. Now, does anyone see time in the second line? No time. But still, there are wave functions and operator, H operator to the energy. So this one is time dependent, this is time independent. Right? Are the symbols for wave functions the same or different? As well as I can type symbols as well as I can recognize them. Is this symbol the same as here, or it's written slightly different? Yeah. Different, right? So here it does depend on time, here it does not. Right? So we have two sorts of wave functions, one that depends on time, another that does not. We have two types of Schrödinger equation, one depends on time, another does not. And it would be reasonable to establish a connection between them. It does exist, we just need to introduce it to ourselves. Okay. And then we have line 3 and 4. I am going to introduce it right now, because who knows if we can squeeze everything literally to the time. So this equation, which I'll skip procedure how we get to it, but I'm sure we'll have time to do it. It includes this H operator, total energy operator, which will include at least, let me jump backwards, which will include at least kinetic energy, which will have second derivative over space. So I'm going forward. So it will be a differential operator or combination of differential operators acting on the unknown function, gives a number, gives again wave function. So it is a differential equation, often with only space variables, no time. So the goal is to solve this differential equation. And now I also would like to throw in another idea from differential equation course. Will you please remind me if you took differential equations in the past? 1, 2, 3, 4, and maybe a couple, thank you, couple of online attendees. So were you solving eigenfunction problems? Yes? Okay, very good. Then you are fully equipped for this course without any, basically you can get full credit and then. So in narrow sense, physical chemistry and quantum theory is just set of eigenfunction problems, which one needs to solve. And also this eigenvalue problem is, you probably saw it in linear algebra, right? When you find eigenvalues of a matrix. Okay, so here is the question, it's not a trick question. How many solutions eigenvalue problem has? Like if I solve a problem like 2x equals 1, linear algebraic with one variable without matrices, it's one equation, one solution, right? If we solve differential equation, eigenvalue equation, how many solutions does it have? Can we say it has 0 solution? Maybe not, then all theory will have. Can you say that it has 1 solution? Who agrees that this equation has one and only one solution? Raise, show like yes, no, or for sure, or you're not sure, you're in doubts. So one solution, doubts, completely no. Anyone else? You can show. I don't care if you will. Okay. So there is a big surprise. So Wyatt was firmly no, and he was correct. So how many solutions this equation has?
That's many.
Did you hear?
That's many, yeah.
So anyone heard what Wyatt told? So infinite number of solutions, and it is very unusual for common sense. So one equation and infinite number of solutions. And right now, it's only introductory slide. I'm not going to prove things right now, but we need to develop a language to speak about one equation with multiple solutions. And here, this index I is counting for the solutions. So the solution includes wave function that we need to find, and also characteristic eigenvalue. And here indices coincide. And if we accept there are many solutions, we can just count them. Phi 1, phi 2, phi 3, right? And if there are numbers, eigenvalues corresponding to it, we can call them E1, E2, E3. Just number everything and then justify that it is correct. So basically, if you think about teaching career, to teach it in like 4-year college for those who are not specializing in this subject, just briefly condense, or even open lesson in high school and squeeze quantum theory in maybe half an hour, this is the slide. It's quite boring, but it is correct. It is just minimalistic set of concepts which is can be introduced as quantum theory. Everything before were foundation, everything after will be applications. And here is actual quantum theory. So enough. I think you're already tired of looking at this introductory slide with strange concepts. So, who is happy to hear the combination of words separation of variables? Who is not happy to hear combination of words separation of variables? Who doesn't care about variables and their separation? Okay, good. So suppose you need to solve differential equation that depends on two independent variables. And it is not a universal method. It may not work. But for broad range of practical applications, it is often possible to present wave function of mathematical function of two variables as product of functions, each of which depends on these independent variables. There is no theorem that it will work all the time, but when it is possible, the solution of partial differential equations is like a piece of cake. If someone may generally like solution of equations, it is as simple as linear differential equation. So it's a pleasant trick that makes life easier. So we are going to, we are not in a math class. We do not need to prove things, but let's assume that everything is good and favorable for us, that this trick is applicable. Let's think that wave function which depends on position and time can be presented in this factorized form. And then we're going to plug it into our Schrödinger equation and look what happens. So capital T is function depending on time, capital X function depending on X. So product of two functions taking derivative of time, derivative of first, second unchanged, first unchanged, derivative of second. What is the derivative of over time of the part that depends on one position? This bracket. Can you tell the answer? Is it clear? Zero. Is it clear why? No. So for the time dependence, for the time variation, for the derivative over time, this function is a constant. It doesn't have dependence on time. And derivative of a constant is zero. Make sense? Then we and then we have on the left side we have this part, and on the right we just reproduce equation as it was. Now, why I'm doing it? Is it, do I want to torture myself? Do I want to torture you? Or I have, do I do it just because I like playing with equations, which is not right? There should be a goal. And the goal was to remove time dependence from the Schrödinger equation, make Schrödinger equation time independent. So I seek an opportunity to remove this capital T. I want legitimately remove T here and remove T there, if it is possible. So I want something that would include this total energy operator, but will not include any memories about time, if it is possible at all. So if a professional mathematician or your teacher of differential equations would attend this course, he would kill me because of lack of rigor. But it is a standard thing just to assume that everything is very favorable, everything is simple and is done in a way that we can process. So let's just assume that this dependence on time has exponential form. If it is not correct, we will realize it very soon, but I hope it is good. So exponential form means it is e to the power t, and just to be general, we put some constant front. So if we try to and why I'm doing so wild assumption? Because the derivative of exponential is exponential itself. So it's all made up. So plugging it here and there, and then derivative of exponential will be, sorry, it's a little blocking, but exponential itself, and then this constant goes up front, right? And here we have exponential as well. Here and there. And if I do this assumption, then we can look on the lower line and see that left and right include e to the power ct. We do not have time derivative anymore because we already practiced time derivative. And then even a rigorous judge will be favorable and merciful if we just cross out this time dependence. In some sense, I already fulfilled my first goal. I did remove time dependence from the Schrödinger equation, right? By assuming that any time dependence is this exponential form. We do not know what is C, but generally we did some mathematical procedure and we did remove. And then it will be C times X, and then this constants, H, and then X. So please remind me, what is X capital here?
The function of position.
Yes, correct. Thank you. So X capital is function of X lowercase. And basically, C X. We already got something that was introduced, right? I need to play a little with constants, but if I call this X as phi of X, and if I multiply left and right by the factors H minus H bar over I, then I will have some number, wave function, the differential operator acting on the wave function, right? So basically, it's already time independent Schrödinger equation. What is the meaning? This question is much more important than mathematical manipulations. So we assumed that time dependence of wave function is removed, and then we got an equation for space distribution of wave function. And we, by referring back to differential equations, we see that it is a sort of equation that has several solutions, multiple solutions, infinite number of solutions. So by solving this equation, we can find what are preferred area of space where electron has higher probability to be found. Right? So in some sense, your not only our common knowledge of SPD orbitals from freshman chemistry is a solution of this equation. If you tell that in one area of space, the probability to find electronic cloud is higher, in another it is lower, and then form these patterns. Make sense? Okay. So just the same thing, just doing over again in different sorts of calligraphy. And here is another aspect how we can glance on this equation. When I was in the undergraduate studies, the words that I'm going to repeat now were offered to me like 20 times. I hated them and was not thinking. But I think that they're not too complicated. They just, I was not caring. So the operator is something that changes wave functions because it multiplies by independent variable, it takes derivatives or something like that. And here's an interpretation of this. We need such wave function that upon acting by operator, it doesn't change. So it is less mathematical, more intuitive interpretation of this equation. So this is an operator of change. It wants to change. We know that like derivative changes everything, or several derivatives changes everything. But there are some favored celebrative wave functions which are not changed upon acting on them with the operator. And the amount of such wave functions is infinite but limited. So not any function will match this property. So for given operator, there are its favorable functions. In some sense, the operator owns these functions. Like, oh, here are my functions, I'm not changing. Right? So own or proper, or in who speaks German? No one? In school? You do?
I took like, yeah, high school German.
So can you try any word in German that would be either own or proper?
Probably not. I
So-
can't remember.
So it's the German word is eigen. And originally this equation was designed in Austria. Schrödinger is from Austria, and he designed the terminology. So he told like those are eigenfunctions and those are eigenvalues. But he was German, so right now it is mix of German and English. Eigenfunctions, eigenvalues, right? So means those functions are own proper, they belong to this operator. If you change operator, set of functions will change as well. Make sense? Okay, and this is a key concept, like key minimalistic concept of the whole course. Who can read this abbreviation? It has nothing to do with teasing people.
Time independence from the
Exactly. Yeah, thank you, Lola. So we did remove time dependence. It's still Schrödinger equation, but it is time independent. So eigenfunctions, eigenvalues. Now we do have 7 minutes more, and I will try to use this time towards making an example. So here is the spiral that we were drawing on the last Wednesday in the lab. And we do have, if you remove, if you do not speak about time dependence, if it is just dependence on the position, we can, on one hand, we can think about accumulation of action and exponential function changing forward as action growing along the trajectory, along the coordinate. One another thing, for getting this pattern, we can have something, and I already used the letter P like momentum, but I still need to justify times x, or one can do like x divided by wavelength, which as long as we progress forward along coordinate, this real and imaginary portions oscillate, and we have this spiral accumulation. So let's use this intuitive knowledge that we have a little bit experience and connect it with concept of eigenvalues. Finding eigenvalue and eigenfunction for a given operator is often a complicated mathematical procedure, not for 7 minutes or maybe already 5 minutes. But we can do reverse engineering. We can take the function and then figure out which operator will like this function, which operator acting on this function will reproduce the function itself. And you know that, you already know the answer. I just need to wrap it up in the legitimate way. You know that taking derivative of space over this exponential will give function itself. But let's just do it a little bit in more details as time allows. So the fringes are offset by the wavelengths, position divided by wavelengths, and here is 2 pi. There was, so here is a little experiment. If one just assumes this format of the spiral and applies, so right now it is yet only later letter P, but later on we will use this letter for momentum. So if you take derivative of position, this everything except x will pop up in front of the exponential. And then if we cancel the function itself, we will see that derivative over position is equivalent to this letter P times I divided by h bar. Maybe what I show is not all founded on step by step, but in here you do not see any wrong derivations, right? It's just derivative. If you assume this shape, apply derivative, then and cancel function, then derivative over position will be this letter P divided by constant multiplied by constant. And this letter P, if we multiply everything by h bar and if you multiply by another I by I is -1, then all this P can be equivalent to derivative over space times constants. So we are approaching the definition of momentum operator. And it's not the whole story. So let me do a little bit more justification. So action is accumulating along trajectory. Spiral can be expressed in terms of wavelength. If we consider everything except x, here we can put action divided by x. Then this action divided by x can be considered as momentum. So it's just gives a hint how to think about it and why we need to use letter P. And dimensions of action are momentum times position. We discussed it in the Bohr model. So here is definition of momentum operator. And by acting this momentum operator on the this so-called plane wave of the wave function in form of exponential, one reproduces function itself. So here P is quantum operator with hat, which takes derivative. And here P is eigenvalue that sets how dense are fringes. So green box is eigenfunction, blue box is eigenvalue, and red box is quantum operator. For the quantum operator of momentum, this exponentially accumulating fringes is the eigenfunction. And the denser the fringes, the bigger is the value of observable of the momentum. Because as these photons, shorter wavelengths, higher energy, higher momentum. Whew. Should be, yeah. So we came to this line. Meeting is done. Everyone is welcome to disconnect and depart. I look forward to see you tonight at 5 in the lab. And I look forward with great enthusiasm to see your slides on Thursday midnight. I'll stay here to answer any questions, but feel free to depart to your next appointment. May, Alison, Josh, do you have any questions?
No.
Okay, thank you. So